Hello, I'm Graham Lewis, and in this short video we're going to talk about permutations, which can be quite a tricky concept at first, so watch the video again if you need, and please ask any questions for someone if you need any help. So imagine we're making a strange salad, and our strange salad has apples, bananas, carrots, and possibly donuts in it. I told you it's a strange salad. Now, what we're going to do now is select 3 of those 4 items. So you're not allowed all 4, you're only allowed 3 of them. So it's a subset and the order matters. Now this is crucial because when you know it's a subset, you know it's either a permutation or a combination question. When the order matters, it's permutation, and when the order is not important, it's combination, which will be dealt with in a different video. So here the order matters because we're going to select 3 of those items and we're going to chop our ingredients in order. So let's start listing in a systematic manner, which is pretty grotty, how we could do this. So for simplicity, let's call apples A, bananas B, carrots C, and D for donuts. Oh, that worked out well, A, B, C, D. So one thing we could do is choose apples, bananas, and carrots. So I've selected 3 and I have apples, bananas, and carrots, and I'll chop in that order. Now imagine the AB is fixed. I could also choose apples, bananas, fixing that, and have donuts. I've exhausted everything with AB, so now I need to go on to a new first pairing. So I'll choose apples and say carrots first, and then I could have bananas, or I could have apples and carrots first, and I could have donuts. And I'll keep going in this systematic manner. I could have apples and donuts in that order, and then I could choose bananas, or I could have apples and donuts and choose carrots. I've now, I think, exhausted everything with A first, AB, or an AC, or an AD. So now I'll go to B first. So I'll have B first, and then say we'll have an A. And I could have carrots, I could have B first and A, and then donuts. And I'm going to carry on counting like that in a systematic manner. I'm going to pause and write all the answers down, but I encourage you, it's good practice to try and get all of the possible permutations using a systematic manner. Okay, so here we go, and I've done the systematic method, and you can see that we actually have 24 different permutations. So by using the systematic way of counting, we've got 24 permutations of taking 3 items in order from 4 items. Wow, this is really tricky, isn't it? And making sure you haven't missed one, etc. So there must be a better way. And there is. And here's a nicer way of doing permutations in kind of like a counting intuitive approach. So what we have is, imagine the first item being selected, and then the second, and then the third. How many choices do we have for the first item? We have 4 choices. We could choose apples, bananas, carrots, or a donut. So 4 for the first one. And then, once we've picked the first one, say we've picked apples, we now only have 3 choices: bananas, donuts, or carrots. So we multiply that by the 3 choices for the second item. And then now we've picked 2 of the choices, so 2 are gone. Say we chose apples and donuts. So now for the very last spot, I have to choose between bananas or carrots. So I have 2 choices. And doing 4 times 3 times 2, whoo, isn't that nice? That comes out much quicker. 24 permutations. So hopefully you understand that, and it's much quicker than listing them all systematically. Let's do another example. Okay, so we've got 12 people on a swimming team, and you choose 4 in a relay, and obviously in a swim team they go in a specific order. You choose carefully who's first, second, third, and fourth, depending on your strength of your swimmers, etc. So how many ways? So the first thing to realize is it's a subset. We're choosing 4 out of 12. So it's not arranging 12 items in a line. So we're choosing 4 from 12. So we know it's a combination question or a permutation question. Then we ask ourselves the question, is order important? Absolutely. We want a specific order, so therefore we know it's not a combination question. We know it's a permutation. So I've got 4 to choose from. Out of the first choice, I've got lots of choice, 12 people. Now 1 person's chosen, so I've only got 11 to choose from for the second spot. Now 2 people have chosen, so only 10. And now the third person's been chosen, so only 9. And 12 times 11 times 10 times 9 is 11,000, 880 ways. Wow, bet you didn't want to do that one the same as we did the first example, writing them all out. We'd be here quite a long time. So really good here, learning how to count by using this method. Okay, now there is another way of doing this using a formula, which I'm going to demonstrate by going back to the first example, and then we'll show it for the second example as well. So if we remind ourselves of the first example, we had a strange salad with apple, bananas, carrots and donuts, and from those 4 items we selected 3 of them and then chose what order to chop them up and then mix them up. So the order matters, we know it's a permutation. Now this symbol here means n items, and we choose r items, and we want to know the number of permutations, hence p. Some people write it this way, and you may see it that way in your calculator. Both are correct, both is fine. I tend to use this one, but as I said, both are correct. So we know that we've got 4 items. That's how many items we've got to choose from, our total number, and we want to select 3 in order. And the order is really important, otherwise it would be a combination question. So I showed you that it was 4 times 3 times 2, which is 24, which was a nice quick way of getting the number of permutations without having to list them all. Now we've got a formula here, and let's see how that's working. So this works, this formula, 4p3, using the formula here, would be substituting in, would be 4 factorial for n. N is 4, r is 3 in this case, so 4 minus 3 factorial, which is equal to 4 factorial over 1 factorial, which does actually equal 24, the same answer. So you can see that the formula is working. Now let's do it for the harder second example we did to show you that the formula works as well. So here on the left we can see how we did the swim team example, and we decided it was 12 times 11 times 10 times 9, giving us 11,880 different permutations. Now let's use the formula. So we'll do 12p4. The 12 counts for, that's your n number, that's your total number of items, and your 4 here is your r number. We're selecting 4, a subset, order matters, so we know it's a permutation. So let's bang those numbers into this formula and let's see what comes out. So we've got 12 factorial on top over 12 minus 4 all factorial on the bottom. So let's just move that over here for a second and we can work it out. So I'm quickly going to write down 12 factorial over 8 factorial, remembering that 12 factorial is 12 times 11 times magic. And there it appears. So we can see that we've got 12 factorial on the top, 8 factorial on the bottom, and look what happens. The 8 divided by 8 cancels, 7 divided by 7 cancels. In fact, 8 factorial, which is sat here, cancels with all of the 8 factorial on the bottom here, leaving you with 12 times 11 times 10 times 9, which is exactly what we had before, 11,880. So another way that you can actually do this question is go straight to your calculator and work out 12p4 to get 11,880 ways. So there's another way of doing it, the formula way or the intuitive way I first showed you. Now let's do another example. This is a nice little question. If minimum is arranged in a line, what is the probability that it starts with MMM? Now, interestingly, the probability is the number of successes over the number of total possibilities. Now, if minimum is actually has to start with MMM, you have no choice. So, because the MMM is always there, you can ignore it because it's there at the beginning. So, actually, what we've got left is, in the word minimum, is INIU. So, all you need to consider is how many ways are there arranging INIU? And the answer to that is you consider them all to be different. So considering them all different, n items in a line, it would be 4 factorial, but 2 of them are the same because I've got 2 i's. So we divide by 2 factorial and we get 12 different ways of arranging INIU. And probability therefore would be 12 out of the total number, which would be 420. Now you're probably thinking, where did I get 420 from? And you might be thinking, how did I get 4 factorial over 2 factorial? I hope so. So let's do the 420 first. So the total number of possibilities for minimum, if you think about it, minimum, I've spelled that right, yep. is there are 1, 2, 3, 4, 5, 6, 7 letters. So imagine they were all different. We would have 7 factorial different ways. But we've got m happening 3 times. So we need to divide by 3 factorial. We've got I happening twice, so we need to divide by 2 factorial, and that comes out at 420. Now, if you're not quite sure why we're dividing by 3 factorial, 2 factorial, let me do you a refresher with the INIU example. So I'm going to imagine I've got INIU, but let's just change that I to a P for now. So I've got INPU. How many different ways are there arranging? And I'm just going to list them all really quickly. So I encourage you to practice doing that. It's good to practice the systematic counting. Make sure you can list all the 24 ways. You can see as before, we've got 4 times 3 times 2 times 1, 4 factorial, 24 ways, which is great. But now let's change the P's back to I's. Now you can see here that I've changed all the P's back to I's. Now let's explore INIU. Have I got any more INIUs? So let's have a look. INIUs. Apologies then, it took me a while to find it. Here it is, and I also noticed I made a mistake. I forgot to put these 2 I's in, so I've corrected that as well. So I've got doubled up on the INIUs. In fact, you picked any of them. Let's pick this one, NIUI. And there you can see another one, cross it out. So we've got half the number. So actually what we've got is 24 ways divided by 2. And how you get that, of course, we discussed it in the other video, is 4 factorial, because imagine all 4 are different, divided by 2 factorial, because 2 are the same, and that giving me my answer 12 different ways. So hopefully that now solves that question that we were just looking at. Want to do another one? How about onomatopoeia? So if we think of onomatopoeia, which is a great English word, what's the probability that it starts with O-O-O-O? So obviously we want to find the total number of successors divided by the total number of possibilities. So firstly, the number of possibilities of how to arrange onomatopoeia with anything is 12 items, so 12 factorial, divided by, we've got 4 O's, so divide by 4 factorial, we've got 2 A's, divided by 2 factorial, and we get this rather large number, 9,979,200. Now, if we want it, so that's our bottom number here, that's the number of possibilities. Now we need to find out the probability, the number of ways of arranging it starting with O-O-O-O. So if we're starting it with O-O-O-O, the O-O-O-O's are fixed. So you can ignore them really. So really we've got 1, 2, 3, 4, 5, 6, 7, 8 items, of which 2 are the same, which is the 2 A's here. And so we've got 20,160. So our final probability of starting with O-O-O-O is 20, that horrible number there. And there we go. That's it in a nutshell. Maybe let's do one more example. Now this is a nice little problem. Imagine we've got those letters B, D, N, S, J, R, M, A, E. Imagine they're standing for people's names like Bertie, Derek, Nora, Shirley, etc. Right, now count the number of different arrangements, but that B, D, N want to be sat together as a group in any order, okay? So basically what we've got here is you think of BDN as one item. So think of BDN as one item. I'll call it F. So instead of BDN, I've got F. And then we've got F, S, J, R, M, A, E. And how many different items have we got? Remember that F there stands for BDN sat together. Well, 1, 2, 3, 4, 5, 6, 7, 7 factorial ways. Because there are 7 factorial ways of doing 7 items, different items in a line. Now, but the problem is BDN can be arranged 3 factorial ways, because you could have BDN or BND, etc. And we know there are 3 factorial ways of arranging BDN. So every one of these 7 factorial ways could be BDN. And now we could have another 7 factorial where instead of Bertie, Derek and Nora sat together, it's Bertie, Nora and Derek in that order. So another 7 factorial way. And obviously we've got 3 factorial ways of arranging BDN. So it's 7 factorial times 3 factorial. So these problems are tricky. We've gone through permutations and different kind of counting when people have to stay together, etc. So please watch the video again at your own pace. They're great fun, these problems. You can think of them in different ways. This video was a bit longer than I intended, but I hope it's helpful. Have a great day. Thank you very much.